Most of the universe is made of something we cannot see. This invisible substance, known as dark matter, is the hidden force that holds our galaxies together and dictates the ultimate fate of the cosmos. By the end of this journey, you will understand the true nature of reality and how a mystery in space could rewrite the laws of physics. We will investigate why stars orbit at impossible speeds without flying apart, and what strange particles might be hiding in the void around us. How do you picture the invisible forces that shape our existence? A galaxy spins so fast its outer stars should be torn away and cast into the emptiness. Yet they hold their course, defying the pull of gravity as we understand it. The only explanation is an unseen presence, a form of matter that exerts a gravitational force but remains completely invisible to our telescopes. This is dark matter. It does not emit, absorb, or reflect any form of light, making it utterly transparent across the entire electromagnetic spectrum. We cannot see it, but we can witness what it does. Its immense gravitational pull acts like an invisible glue, providing the extra force needed to keep those fast-moving stars safely in their galactic orbits. Think of it as the cosmic scaffolding, the unseen framework upon which galaxies are built. Without this hidden architecture, the universe would be a far more barren and disorganized place. Galaxies might never have coalesced from the primordial gas, and the vast cosmic web of brilliant filaments and immense voids would simply not exist. This is not a minor ingredient. Dark matter is the dominant architect of all cosmic structure, its silent gravitational hand shaping everything from the smallest, faintest dwarf galaxies to the largest assemblies of matter in the universe. To truly grasp its importance, we must look back at the first clues that revealed this missing mass was there at all. The story of dark matter's discovery begins not in deep space, but with a brilliant and often contentious astronomer named Fritz Zwicky. In the 1930s, Zwicky turned his attention to the Coma cluster, a dense swarm of galaxies millions of light-years away. He measured how fast these galaxies were moving around the cluster's center, and the numbers he found were staggering. The galaxies were racing so fast that, according to the laws of gravity, the collective pull of all the visible stars and gas should have been utterly insufficient to hold the cluster together. The entire system should have flown apart. Zwicky concluded there had to be hundreds of times more mass present, an invisible substance providing the necessary gravitational glue. He gave this mysterious material a name, Dunkel Materie, dark matter. Yet for decades, his radical proposal was dismissed by most of his peers. The case for this missing mass remained a curious footnote until the 1970s, when astronomer Vera Rubin delivered the evidence that could no longer be ignored. She meticulously mapped the rotation of spiral galaxies, charting how fast stars orbit at different distances from the galactic center. According to Newton's laws, stars on the outer edges, far from the central bulge of mass, should orbit much more slowly, just as Pluto trudges slowly around the Sun compared to the inner planets. But Rubin found something completely different. The stars in the outer reaches of galaxies were moving just as fast as those near the center. It was as if the entire galaxy was a solid disk spinning as one. The only logical explanation was that each galaxy was embedded within an enormous, invisible sphere of matter, a halo whose gravity was pulling on the outer stars, speeding them up. This halo was dark matter. These pioneers faced immense skepticism, their work challenging the very foundations of physics, yet their persistence revealed a fundamental truth. The universe we see, the glittering tapestry of stars and galaxies, is just a small fraction of what is actually there. The visible cosmos is like the foam on the surface of a deep, dark ocean, with most of the substance lying hidden beneath. The quest Zwicky and Rubin began has now become one of the greatest scientific endeavors of our time. So what is the modern evidence that has cemented dark matter as a cornerstone of our cosmic understanding? Einstein's theory of general relativity gave us a new way to see the unseen. It predicted that massive objects warp the fabric of space and time, and that light traveling through this warped space does not always move in a straight line. Its path can be bent. This phenomenon, called gravitational lensing, is one of the most powerful tools we have for mapping dark matter. Think of space as a vast, taut rubber sheet. Place a heavy bowling ball on it, and the sheet dips. Now roll a tiny marble past the bowling ball. The marble's path will curve following the dip in the sheet. In the cosmos, the bowling ball is a massive object like a galaxy cluster, and the marble is a beam of light from a galaxy billions of light years behind it. The gravity of the cluster bends the light's trajectory, acting as a colossal lens. This cosmic lens can distort the background galaxy into multiple images, stretch it into brilliant arcs, or even form a perfect circle of light known as an Einstein ring. But here is the crucial part for our detective story. The amount of bending we see depends on the total mass of the foreground cluster. When astronomers calculate the mass of the visible stars and gas, it is never enough to create the dramatic lensing effects they observe. The only explanation is a vast amount of invisible mass, dark matter, providing the extra gravitational pull. This allows us to literally map the shape and distribution of something we cannot see. A stunning example of this is the Bullet Cluster, a cosmic collision of two galaxy clusters. During this violent event, the clouds of hot gas, the normal matter that we can see with X-ray telescopes, slammed into each other, slowing down and heating up. But the dark matter, as revealed by gravitational lensing maps, did something entirely different. It passed right through the collision, seemingly unaffected. The dark matter and the normal matter were physically separated. This was a direct observation that dark matter does not interact with itself or normal matter in the way that particles of gas do. It is truly collisionless, a ghostly substance that feels gravity but little else. Gravitational lensing has given us eyes for the invisible. It reveals the hidden architecture of the universe, showing us the dark matter scaffolding that holds the cosmic web together. This technique confirms that dark matter is not a single anomaly, but a pervasive presence, its gravitational footprint etched into the light from the farthest reaches of space. Gravitational lensing gives us a map, but to read that map is to see a breathtaking design. The cosmos is not a random scattering of stars. It is structured, organized on the grandest possible scale into a magnificent architecture known as the cosmic web. Picture brilliant galaxies not as isolated islands, but as glittering nodes connected by vast, invisible filaments, all suspended within immense, empty voids. This entire structure, this cosmic web, is built from dark matter. It is the unseen skeleton upon which the visible universe is draped. How did this intricate tapestry come to be? The story begins in the fiery aftermath of the Big Bang, when the universe was a nearly smooth soup of particles. But it was not perfectly smooth. Tiny, random fluctuations in density, smaller than 1 part in 100,000, were imprinted on the cosmos. These minuscule ripples were the seeds of all future structure. Dark matter, feeling only the force of gravity, began to clump around these seeds first. Because it does not interact with light or push back with radiation pressure, it could start collapsing long before normal matter could. Over billions of years, gravity relentlessly amplified these small clumps. Dark matter formed an invisible scaffolding of potential wells, vast gravitational basins. Ordinary matter, the gas that would become stars and galaxies, was then simply pulled along for the ride. It flowed into these dark matter halos where it could cool, condense, and finally ignite into the first brilliant stars. We can witness this process through sophisticated computer simulations that model the evolution of the universe. The most famous of these, the Millennium Simulation, runs the clock forward from the early universe to the present day. When scientists run this simulation with only the normal matter we can see, the result is a disappointingly bland cosmos, lacking the rich web of clusters and filaments. But when they include the gravitational influence of dark matter, the simulation perfectly recreates the cosmic web we observe through our telescopes. The visible galaxies trace out the underlying dark matter skeleton like lights on a hidden highway. This large-scale structure is one of the most compelling lines of evidence for dark matter's existence and its dominant role. It shows us that dark matter is not merely a ghostly presence within individual galaxies, but the fundamental architect of the universe itself, its gravitational hand guiding the formation of everything we see. To understand how this hidden force first took hold, we must journey back to the very beginning. The first moments of the universe were a seething, opaque plasma, a state of matter so dense that light could not travel freely. Within this primordial fireball, the fate of dark matter was sealed. Its defining characteristic, its ghostly nature, came from a pivotal event known as decoupling. While particles of ordinary matter, like protons and electrons, were constantly buffeted by radiation, dark matter particles slipped away from the chaos. They stopped interacting frequently with anything else, becoming gravitational islands in a raging sea. This early disconnection was a cosmic head start. Freed from the pressure of radiation, dark matter could immediately begin to respond to the gentle pull of gravity, starting to clump together around the tiniest ripples in the fabric of space. Normal matter, still trapped in a constant push and pray with light, could not begin to collapse until much later, hundreds of thousands of years after the Big Bang. By that time, dark matter had already laid the groundwork, sculpting vast, invisible gravitational wells ready to catch the falling gas of the first galaxies. We have a baby picture of this universe, a snapshot of that moment when normal matter finally broke free. This is the cosmic microwave background, a faint glow of radiation that fills all of space. It is the afterglow of the Big Bang itself. This relic light is not perfectly uniform. It contains tiny variations in temperature, patterns of hotter and colder spots that are a frozen record of the universe's infant geometry. The size and distribution of these spots are a precise cosmic recipe, telling us exactly how much ordinary matter, and dark energy the universe contains. The patterns we see are impossible to explain without a significant amount of dark matter, a substance that was already pulling on the young cosmos long before the first star ever shone. This primordial evidence confirms that dark matter is not a modern addition, but a fundamental ingredient from the very beginning, the unseen director that guided the formation of the cosmic stage. But what is the identity of this ghostly director? What kind of particle could possess such profound influence while remaining so utterly elusive? For decades, one particular suspect has stood out in the lineup of theoretical particles, a candidate so promising it earned a nickname, the WIMP. This stands for Weakly Interacting Massive Particle. The name itself tells you almost everything you need to know. These are hypothetical particles thought to be heavy, perhaps 100 times the mass of a proton, and they interact with normal matter only through the weak nuclear force and gravity. This makes them incredibly ghostly, passing through the entire Earth as if it were not even there. The the case for WIMP became incredibly strong due to what physicists call the WIMP miracle. It is a stunning cosmic coincidence. Calculations show that if such particles were forged in the hot, dense conditions of the Big Bang, and if they had the right mass and weakness, they would have naturally frozen out into exactly the abundance of dark matter we observe in the universe today. It is as if the universe left us a perfect recipe, and WIMP fit it exactly. This elegant solution has driven a monumental, global hunt. To have any hope of detecting such a faint whisper of an interaction, scientists have built extraordinary laboratories deep underground. Places like the Sanford Underground Research Facility in South Dakota, where the LUX and LZ experiments reside, are buried beneath a mile of rock. This immense shield blocks out the constant rain of cosmic rays from space, creating a silence profound enough that researchers can listen for the tiny ping of a WIMP striking the nucleus of an atom in their ultra-pure liquid xenon detectors. For years, experiments like LUX, Xenon, and Panda X have pushed their sensitivity to staggering limits, searching for a signal that has never come. They have ruled out vast swaths of possible WIMP properties, yet the detectors remain silent. This absence of evidence is not a death knell, however. WIMP remain compelling because they are not just a random guess. They emerge naturally from elegant theories that seek to extend our standard model of particle physics, most notably supersymmetry. This theory proposes that every known particle has a heavier superpartner, and the lightest of these superpartners has all the right properties to be a stable, weakly interacting dark matter particle. The search for WIMP is a story of brilliant engineering and profound patience, a decades-long experiment at the very frontier of what is detectable. But as the silence from the deep underground laboratories continues, the spotlight has begun to shift. While WIMP represent a hunt for a heavy ghost, another compelling candidate is almost unimaginably light. Axions are theoretical particles born from a completely different puzzle in physics, the strong CP problem. This issue deals with a surprising symmetry in the laws that govern nuclear forces, a symmetry so perfect that physicists find it suspicious. The axion was proposed to explain why this symmetry exists, and in doing so, it accidentally provided a perfect candidate for dark matter. These particles would be billions of times lighter than an electron, so featherweight that they would behave less like discrete particles and more like a pervasive, wave-like fluid filling the cosmos. In the early universe, this fluid could have been produced in enormous quantities, forming a cold, coherent field that perfectly matches the properties we require for dark matter. Detecting such an ethereal substance demands extraordinary ingenuity. Experiments like the Axion Dark Matter Experiment, or ADMX, function like the most sensitive radio receivers ever built. They use powerful, steady magnetic fields with the hope that an axion passing through would convert into a faint but detectable microwave photon. Researchers must meticulously tune their instruments, scanning through millions of possible frequencies, listening for a whisper of a signal from the dark matter halo that envelops our own Milky Way. The appeal of the axion is its elegant duality. A single discovery would solve two profound mysteries at once, revealing the nature of dark matter and fixing a deep-seated issue in our understanding of subatomic physics. This search highlights a vital truth in science. The ultimate answer may not come from where we initially expected. The persistent silence from WIMP detectors has encouraged physicists to broaden the hunt, to consider that the invisible backbone of the cosmos could be built from something far lighter and more strange than we first imagined. Yet there is an even more radical possibility. What if we have been misinterpreting the clues all along? What if the missing mass is not a particle at all, but a sign that our understanding of gravity itself is incomplete? But what if the ghost is not a particle? What if the entire cosmic detective story has been chasing a phantom, and the real culprit is a flaw in our most fundamental laws? This radical possibility has a name: modified Newtonian dynamics, or MND. Proposed in the 1980s by physicist Mordechai Milgrom, this theory suggests a simple yet profound alteration. It claims that gravity does not follow Newton's or even Einstein's rules in every situation. In the deep quiet of interstellar space, where accelerations become incredibly faint, gravity gains a subtle, extra strength. This boost would be enough to whip the outer stars of a galaxy to their observed speeds, all without needing a single particle of dark matter. Imagine the difference between pushing a shopping cart on smooth pavement versus through thick mud. MND suggests that in the cosmic equivalent of thick mud, the extremely low acceleration environment of a galaxy's outskirts, gravity gets a better grip. It is an elegant solution that perfectly explains the rotation curves of individual galaxies, the very problem that first revealed the missing mass. For its supporters, it is a more straightforward answer, one that does not require inventing an entirely new, invisible form of matter that has evaded detection for decades. Yet, for all its success on the galactic scale, MND faces its own formidable challenges. It struggles to explain the bullet cluster, where the gravitational lensing clearly shows mass separated from the visible gas. It cannot easily account for the precise patterns in the cosmic microwave background, the universe's baby picture, which strongly points to the presence of a substantial amount of unseen matter that existed long before galaxies formed. While modified gravity theories like MND represent a brilliant and necessary challenge to the mainstream, most cosmologists find that dark matter provides a more complete story. It is a single, unifying actor that can play every role, from sculpting the large-scale cosmic web to enabling the formation of the very first galaxies. This ongoing debate is not a weakness of science, but its greatest strength. It is a rigorous, high-stakes competition of ideas, where every new telescope and deep underground experiment serves as a judge. This tension pushes our understanding to its limits, forcing us to ask deeper questions about the nature of gravity, matter, and reality itself. To see why dark matter remains the leading actor, we must watch it perform its most crucial role, building the cosmic structures that would eventually become our home. Dark matter halos are the invisible engines of galaxy formation. Think of them as deep, gravitational potholes forming in the smooth, expanding road of the early universe. While the hot plasma of normal matter was still too energetic to settle down, dark matter, unaffected by light's pressure, was already collapsing into these dense knots. Each halo became a cosmic catchment basin, a trap for the raw material of creation. Vast streams of primordial hydrogen and helium gas, the baryonic matter, were pulled inexorably into these gravitational wells. As the gas fell, it compressed, collided, and began to shed its immense energy, cooling down over millions of years. This cooling was the crucial next step. It allowed the gas to condense further, fragmenting into dense clouds that, under their own weight, ignited into the first brilliant stars. These were the seeds of the very first galaxies, all cradled within the protective grasp of a dark matter halo. This partnership was not a one-time event but an ongoing dance. The dark matter halo provides the stable, deep gravitational potential that keeps a galaxy from flying apart, while the ordinary matter within it lives a much more dramatic life. Stars are born, they shine, and they die in violent supernova explosions. These cataclysms blast gas back out into the halo, enriching it with heavy elements and stirring up the potential for new star formation. Supermassive black holes at the galactic centers add their own powerful feedback. emitting intense radiation and jets that can heat surrounding gas and regulate further growth. This intricate interplay between the invisible anchor of dark matter and the vibrant, chaotic physics of normal matter is what creates the stunning diversity of galaxies we see, from orderly spirals to giant ellipticals. Without the dark matter framework, this process would have been achingly slow and disorganized. The universe might be a dim, sparse place, with gas struggling to coalesce and few galaxies ever lighting the cosmic dark. The very nature of the dark matter itself leaves a distinct fingerprint on the galaxies that form. The leading model, known as cold dark matter, posits particles moving sluggishly in the early universe. This slowness allows it to clump efficiently on very small scales, creating a rich hierarchy of structure. This model makes a clear prediction. Our own Milky Way galaxy should be surrounded by hundreds of small satellite galaxies, tiny clumps of stars, each held in its own tiny dark matter halo. And indeed, with powerful telescopes, we are finding more and more of these faint satellites, just as the cold dark matter theory foretold. An alternative idea, warm dark matter, made of faster-moving, lighter particles, would have washed out these small-scale structures, leaving far fewer dwarf galaxies. The fact that we observe these tiny galaxies is a powerful clue that dark matter is likely cold, giving us a vital detail about the identity of this mysterious substance. The grandest spirals and the faintest dwarfs all tell the same story. They are the visible offspring of an invisible parent. To see dark matter's influence at its most extreme, we must look to the smallest and most dark matter-dominated galaxies in the cosmos. These faint, ghostly satellites are the ultimate dark matter laboratories. Dwarf galaxies are the smallest and most numerous galaxies in the universe, and their true nature reveals a startling fact. They are not held together by their own starlight, but by the immense, invisible grip of dark matter. In these tiny realms, the hidden substance is not just a component, it is the main event. For every ounce of visible matter in the form of ancient, faint stars, there can be hundreds or even thousands of times more mass in dark matter. Consider the Draco Dwarf, a small spheroidal galaxy orbiting our own Milky Way. It is so dim you could look right through it, yet its stars move at velocities that demand a tremendous gravitational anchor. The mass-to-light ratio is staggering. It must be composed almost entirely of this mysterious, unseen mass. This incredible dominance makes these faint galaxies perfect hunting grounds, since they are so rich in dark matter and relatively clean of the confusing background noise from other astrophysical processes. Scientists use them to search for indirect signals of dark matter particles. The theory is that when two dark matter particles collide, they might annihilate each other, transforming into a flash of gamma rays or a spray of other standard particles we can detect. Telescopes scan the skies, focusing on the hearts of these dark matter-dominated dwarfs, hoping to catch a telltale flicker of this self-destruction in the void. Their very existence is a triumph for the cold dark matter model. The cosmological simulations that map the growth of cosmic structure predict that thousands of these small dark matter halos should swarm around a large galaxy like our own. And with patient observation, we have found them, dozens of these ultra-faint dwarfs, each a tiny island of stars adrift in a vast sea of invisible matter. Yet, these tiny galaxies also present a profound puzzle known as the too big to fail problem. The most sophisticated simulations predict that some of these dark matter halos should be so massive and dense that they would inevitably attract enough gas to form bright, star-filled galaxies we could easily see. But when we look, those expected bright satellites are missing. The halos seem to be there, but they are largely dark and barren. This is not a refutation of dark matter, but a crucial clue. It tells us that our understanding of how gas cools, how stars form, and how supernova can blow that gas away within these tiny halos is incomplete. The interplay between the dark matter scaffolding and the complex physics of normal matter is more subtle than we first imagined. By studying these faintest of galaxies, we are not just confirming the presence of dark matter, we are learning about its specific properties and how it orchestrates the birth and evolution of all cosmic structures. These tiny, dark-dominated realms hold monumental secrets, forcing us to refine our most fundamental models of the universe. To see dark matter's power on a truly colossal scale, we must leave these faint dwarfs behind and journey into the heart of immense galaxy clusters. Galaxy clusters are the universe's ultimate monuments, colossal cities of light and gravity where dark matter's power is on full display. These are not simply random gatherings of galaxies. They are the largest structures held together by gravity in the entire cosmos, each one a sprawling metropolis containing hundreds or even thousands of individual galaxies, all immersed in a seething ocean of multimillion-degree gas and anchored by a deep, invisible well of dark matter. To grasp their immense scale, consider that the hot gas within a single cluster often contains more normal matter than all of its stars combined. Yet even this vast reservoir of glowing plasma is just a fraction of the story. When we add up the mass from all the visible components, the stars and the gas, we find it accounts for a pitifully small portion of the cluster's total weight. The rest, the overwhelming majority, is the silent presence of dark matter. We know this from multiple, independent lines of evidence that all point to the same staggering conclusion. The random motions of the galaxies within the cluster are so fast that without a tremendous amount of extra gravity, they would escape, flying off into the void. The intense heat of the X-ray emitting gas similarly requires a deep gravitational well to contain it, a well far deeper than visible matter alone can provide. And most directly, the way these clusters bend the light from more distant galaxies, a phenomenon known as gravitational lensing, draws us a precise map of their total mass. This map consistently reveals an immense, smooth halo of invisible matter enveloping the entire cluster, a ghostly titan holding the brilliant city together. The bullet cluster stands as a definitive piece of evidence. In that cosmic collision, our maps show the dark matter, traced by its lensing effect, clearly sailing ahead of the clouds of hot gas that were slowed by their own violent interaction. This separation is a direct demonstration that dark matter is not only invisible but profoundly collisionless, passing through itself and normal matter with ghostly ease. These colossal mergers do more than just prove dark matter exists. They act as natural particle accelerators on a cosmic scale, creating environments of immense energy where we might finally catch a signal from dark matter particles annihilating or decaying. By carefully observing these giants, cosmologists can take a cosmic census, precisely measuring the total amount of dark matter in the universe and refining our understanding of how all structure, from the smallest dwarf galaxy to the largest supercluster, came to be. The silent architecture of these clusters provides the ultimate testing ground for our theories, challenging us to explain the invisible force that built them. But to move from mapping its influence to truly identifying it, scientists must attempt the seemingly impossible: to catch a single dark matter particle here on Earth. Deep beneath the mountains of Italy, in a cavern shielded from the cosmic noise of the surface, a vat of liquid xenon waits in perfect darkness. This is the heart of the Xeno-NNT experiment, a place of almost impossible purity, where scientists listen for the faintest whisper in the universe. Their goal is audacious: to feel the gentle nudge of a single dark matter particle as it drifts through the Earth. These direct detection experiments are the most intimate form of the hunt, an attempt to shake hands with the ghost. The entire premise rests on a staggering statistic. Billions of these invisible particles are likely streaming through your body every second, a cosmic wind you cannot feel. Most pass through the entire planet as if it were empty space, but very, very rarely one might just graze the nucleus of an atom. In a detector filled with ultra-pure liquid xenon, such a collision would produce a tiny flash of light and a wisp of electrical charge, a dual signal that could betray the particle's presence. To hear that whisper, you must create a profound silence. Laboratories like Xenon NNT and its American counterpart, LZ in South Dakota, are buried under a mile of rock. This natural shield blocks out the constant barrage of cosmic rays and other radiation that would drown out the elusive dark matter signal. The detectors themselves are marvels of engineering, built from materials selected for their incredible radio purity to ensure that their own components do not create false alarms. For years, these experiments have been growing larger and more sensitive. Xenon NNT uses over 8.6 tons of liquid xenon, a massive target to increase the odds of that one in a trillion interaction. Yet, despite this scale and sensitivity, the detectors have remained silent. They have not found the signal they were built to discover. This silence is not a failure, it is data. Each empty run, each day without a detection, helps physicists draw a map of what dark matter is not. They have ruled out vast territories of possible mass and interaction strength for particles like WIMP, constraining the theoretical landscape and forcing new ideas to the forefront. The challenge is almost beyond comprehension. Scientists are searching for an interaction so feeble it could be masked by the gentle decay of a single atom of trace radioactivity in the detector walls. It requires patience on a cosmic scale, running these exquisite instruments for years to gather enough exposure to have a chance. The perseverance is a testament to the scientific drive to know, to reach out directly into the dark and see if something reaches back. A confirmed signal would be an epoch-making discovery, instantly transforming our understanding of the universe's fundamental ingredients. But since the ghost has not yet spoken in the deep underground labs, we must also search for its shadow elsewhere by watching for the debris it might leave behind in the void of space. While underground labs listen for a whisper, other scientists scan the skies for a scream. This is the hunt for indirect detection, a search not for the dark matter particle itself, but for the debris it might leave behind. The theory is elegant. If dark matter is its own antiparticle, then when two particles meet, they could annihilate each other in a flash of energy, transforming into something we can see, like a burst of gamma rays or a shower of other standard particles. Think of it as trying to find a ghost by looking for its footprints rather than the ghost itself. The entire cosmos becomes our laboratory, with natural dark matter hotspots serving as the experiment. The center of our own Milky Way galaxy is one such prime hunting ground. It is thought to contain an incredibly dense concentration of dark matter, a place where collisions should be frequent. Orbiting high above Earth, the Fermi Gamma Ray Space Telescope has spent years staring at this region, meticulously counting gamma ray photons, and it found something intriguing, an unexplained excess of gamma rays emanating from the galactic center. The energy signature of this glow is tantalizing, matching what some models predict for dark matter annihilation. Yet, the case is far from closed. This mysterious signal could also be produced by a population of unseen pulsars, the rapidly spinning corpses of dead stars. Teasing apart a potential dark matter signal from the cacophony of known astrophysics is one of the greatest challenges in modern astronomy. To strengthen the case, scientists look for the same signal in cleaner environments. Dwarf spheroidal galaxies, those faint satellites of the Milky Way, are perfect for this. They are teeming with dark matter, but have very few of the conventional astrophysical sources that could create confusing background noise. When Fermi looks at these dark, quiet dwarfs, it does not see a strong, definitive gamma-ray excess. This absence is itself a powerful clue, helping researchers rule out certain masses and interaction rates for dark matter particles. Meanwhile, a different kind of experiment is underway on the International Space Station. The Alpha Magnetic Spectrometer, or EMS-02, is a sophisticated particle detector mounted on the station's exterior. It does not look for light but for cosmic rays, the high-energy particles that constantly rain down from space. EMS-02 has measured a curious excess of positrons, the antimatter counterparts to electrons. While this, too, could be a sign of dark matter annihilating in the halo of our galaxy, it could also be explained by more mundane sources, like pulsars accelerating particles across the galaxy. The beauty of indirect detection is its ability to probe a wide range of possible dark matter particles, including some that would be too light or too weakly interacting to ever be found in an underground tank on Earth. A confirmed signal from the sky would be a monumental discovery. It would not only prove that dark matter exists as a particle, but the specific energy of the gamma rays or the pattern of cosmic rays would tell us its mass and how it interacts with itself. This global effort turns the heavens into a colossal high-energy physics experiment, where every unexplained flicker of light or anomalous particle holds the potential to illuminate the dark. To complete the search, scientists are not just waiting for signals from space or underground. They are trying to create dark matter right here on Earth. Buried under the Swiss-French border, a circular tunnel 27 kilometers long houses the most powerful particle accelerator ever built. The Large Hadron Collider takes the search for dark matter in a radically different direction. Instead of waiting for a ghost to drift through a detector or scanning the skies for its annihilating glow, this colossal machine tries to create dark matter from pure energy. It smashes beams of protons together at velocities infinitesimally close to the speed of light, recreating for a fleeting instant the fiery conditions of the early universe. In this primordial chaos, the hope is that new particles never before seen will flash into existence. Among them could be the very constituents of dark matter. The detectors surrounding these collision points, monumental experiments named Atlas and CMS, are like the most high-speed, high-resolution cameras ever conceived. They capture the aftermath of these tiny, violent explosions, tracking every known particle that sprays out from the epicenter. But how do you see something that is fundamentally invisible? The signature of dark matter is not what the detectors see, but what they miss. Physicists meticulously account for all the energy and momentum before and after a collision. If a significant amount of energy simply vanishes, carried away by a particle that left no trace in the sensors, that missing energy becomes the ghost's calling card. It is the smoking gun for an invisible entity, like deducing a thief's presence by the empty space where a jewel once was. This hunt is deeply connected to theories like supersymmetry, which elegantly predicts a whole new family of particles. The lightest of these superpartners would be stable, neutral, and weakly interacting, a perfect WIMP candidate that could have been streaming through the LHC's detectors for years, leaving only a telltale deficit of energy in its wake. So far, no definitive signal has emerged. The detectors have not recorded a pattern of missing energy that cannot be explained by known processes. Yet this absence is not a failure. Each null result carves away another piece of the theoretical landscape, telling physicists what dark matter is not, and forcing them to refine their models and consider new possibilities. The power of a collider is its ability to probe a different realm entirely. It can potentially create dark matter particles that are so weakly coupled to normal matter they would be utterly undetectable in a deep underground tank. Particles that would never annihilate in space to produce a gamma-ray signal. The collider creates them right in front of us, if only for a moment, and their silent escape is the very evidence we seek. This relentless, multi-pronged attack, combining the deep silence of direct detection, the celestial whispers of indirect observation, and the brute force creation of colliders, forms a powerful synergy. Each approach covers the other's blind spots, building a comprehensive net to catch a ghost. As the LHC continues its runs and plans for even more powerful future colliders take shape, the energy frontier pushes ever forward. The next collision could be the one that creates a particle from the dark sector, finally revealing the hidden architecture of our reality. Where will this unprecedented discovery come from, and what new machines are being built to finally see the unseen? The silence from today's detectors is not an end, but a call to build something even more sensitive. Across the globe, a new generation of experiments is taking shape, engineered to listen for whispers so faint they defy current imagination. The direct detection hunt is scaling up to a monumental level with projects like Darwin. Imagine a vat of liquid xenon not weighing 8 tons but 50. This colossal target, kept in even deeper silence, would be so vast and pure that it could finally hear the gentle nudge of a WIMP or rule out its existence for good. It is a machine built on the edge of possibility, designed to probe the most elusive interactions predicted by theory. Simultaneously, the search for the featherweight action is broadening its reach. Experiments like ADMCs are evolving into full-scale observatories, meticulously tuning through millions of possible frequencies. They are scanning the cosmic radio dial with breathtaking precision, listening for the specific station where an action might announce its presence. This is not a passive wait, it is an active, systematic sweep through the realms of the possible. Above us, in the pristine quiet of space, a different kind of hunter is at work. The Euclid Space Telescope is not looking for particle collisions, it is mapping the invisible. By observing the subtle distortions of billions of galaxies, Euclid will create the most detailed chart of the cosmic web's dark matter skeleton ever made. This grand map will measure the hidden scaffolding's properties with such accuracy that it could reveal if dark matter has any unexpected, wispy interactions with itself, a quality that would profoundly reshape our models. The technological frontier is also exploding with new ideas. Scientists are developing ultra-sensitive quantum sensors and exotic materials that can detect vibrations from dark matter particles billions of times lighter than WIMP. These devices are so precise they could feel the gentle breeze of a single particle as light as a grain of dust. From the depths of an Italian mountain to the silence of space, this is a global endeavor fueled by a shared, relentless curiosity. Each new machine, each more ambitious than the last, represents a pathway through the unknown. The future of this search is not a single thread, but a brilliant tapestry of methods, any one of which could finally illuminate the dark. This incredible experimental persistence is guided by a crucial question. What theoretical maps are we using to navigate this vast unknown territory? Theoretical physics builds the maps that guide our search through the dark. These are not wild guesses, but intricate frameworks born from a desire to solve the deepest puzzles of the cosmos. Among the most elegant is supersymmetry, a concept that proposes a fundamental symmetry in nature. It suggests every particle we know, every electron and quark, has a heavier superpartner. In this mirrored world, the lightest of these superpartners would be stable, neutral, and interact only feebly with normal matter. It is, in essence, the perfect theoretical candidate for a WIMP, a natural solution that emerged from efforts to unify the forces of nature. This elegant idea also tackles another profound mystery, the hierarchy problem, which questions why gravity is so unimaginably weaker than the other fundamental forces. Supersymmetry offers a beautiful resolution, but so far, the Large Hadron Collider has not found the superpartners it predicted. This silence has forced theorists to broaden their horizons, to consider even more exotic landscapes. Some models propose that our universe has more than the three spatial dimensions we experience. In these theories of extra dimensions, dark matter could be a particle that propagates through these hidden realms, forever confined to a parallel reality that touches our own only through the universal force of gravity. It would be a ghost from another dimension, its presence felt only by its gravitational shadow. Another compelling idea is that of a hidden sector, a whole family of particles that barely talk to our own. In this scenario, dark matter might interact with normal matter not through the weak force, but through a new, incredibly faint force carried by a hypothetical particle, a dark photon. This would create a secret channel of communication between the visible and invisible worlds, a whisper so soft we are only now building instruments sensitive enough to hear it. The incredible diversity of these models is not a sign of confusion, but a testament to the creative power of theoretical physics. Each framework is motivated by a desire to solve multiple puzzles at once, weaving dark matter into a larger tapestry that explains the universe's deepest workings. While none have been confirmed, they provide specific, testable targets for our experiments. The relentless silence from detectors and colliders is not a dead end. It is a dialogue. Each null result forces theorists to refine their models, to explore new corners of the mathematical landscape. This dynamic dance between prediction and observation is the engine of discovery, narrowing the path toward a final answer. This profound quest does more than just fill a gap in our equations. It forces us to confront fundamental questions about our place in the cosmos and the very nature of reality. This invisible substance has seeped from scientific journals into the very fabric of our stories. Science fiction has eagerly adopted dark matter, transforming it into a canvas for our deepest cosmic fears and fascinations. In novels, films, and video games, it is rarely portrayed as a simple, inert particle. Instead, it becomes a source of limitless energy, a gateway to other dimensions, or even a form of alien intelligence. One of the most profound fictional explorations is found in Philip Pullman's His Dark Materials trilogy, where he renames dark matter as dust. In his universe, dust is not a passive gravitational glue, but a conscious, fundamental particle intimately connected to human consciousness and the existence of parallel worlds. While this is a work of imagination far from our current scientific understanding, its power lies in how perfectly it captures the profound sense of mystery that real dark matter evokes. It personifies our intuition that this hidden component of the cosmos must be deeply significant, that its discovery will reveal more than just missing mass, but something fundamental about existence itself. This cultural resonance serves a vital purpose. By giving a name and a narrative to the invisible, it bridges the immense gap between the complex mathematics of cosmology and a public sense of wonder. When a viewer watches a spaceship in a movie harness dark matter for a faster-than-light jump, or a gamer collects it as a rare resource in a virtual universe, they are participating in a cultural conversation about the universe's unknowns. This fascination is not just entertaining, it is inspirational. It fuels public interest, which in turn supports the funding and the next generation of scientists needed to continue the real-world hunt. The stories we tell about dark matter reflect a timeless human drive to personify the void, to fill the emptiness with meaning and possibility. They remind us that the greatest scientific mysteries inevitably become cultural touchstones, challenging our perception of reality not just in labs but in our collective imagination. This cultural journey mirrors the scientific one, both asking the same fundamental question: what does it mean to live in a universe where most of reality is hidden from our senses? Our entire experience of reality is built upon a fragile premise that what we can see and touch constitutes the whole of what is real. Dark matter shatters this assumption with a simple, staggering fact. The universe we perceive, the grand tapestry of stars and galaxies glowing in the night sky, represents less than 1/5 of all the matter that actually exists. We are like deep-sea creatures who have only ever known the pressure of the water, completely unaware of the vast, air-filled world above the surface. Our primary senses and even our most powerful telescopes are tuned to the electromagnetic spectrum. We see the world through light, but dark matter does not play by those rules. It is a reality that operates on a different frequency, one of pure gravity, forever beyond the reach of our eyes and our instruments. This forces a profound philosophical shift. What we call reality is merely the fraction of the cosmos that interacts with light. The rest, the true bulk of the cosmic landscape, is a silent, invisible realm we can only know through its gravitational shadow. This is not so different from the long history of inferring unseen entities. For centuries, scientists knew about atoms not because they could see them, but because they could observe their effects, the way they explained the behavior of gases and the bonding of elements. Atoms were theoretical constructs long before we had microscopes powerful enough to image them. Dark matter is walking the same path, a modern testament to the power of human reason. We observe a galaxy spinning too fast and deduce the presence of an invisible anchor. We see light bending around nothing and map the shape of the unseen. This process, the scientific method in its purest form, is a tool for transcending our biological limits. It allows us to uncover truths that are fundamentally inaccessible to our direct senses. This journey is also a lesson in profound humility. Every time we believe our model of the universe is nearly complete, a new anomaly arises, a new crack appears in the foundation. Dark matter is one of the largest cracks we have ever encountered. It reminds us that our knowledge is always provisional, always subject to revision by the next great discovery. The mystery does not represent a failure of science, but its ultimate success, a demonstration of its relentless drive to question, to test, and to look beyond the obvious. The search for this hidden world invites us to expand our very definition of existence. To know something does not always require that we can touch it or see it glow. Sometimes we know it by the gentle, persistent pull it exerts on everything around us. This philosophical perspective transforms the hunt from a technical puzzle into a deeper quest to understand our place in a cosmos where most of the substance is forever hidden. With this broader view of reality in mind, we must now ask what role this invisible architect plays in the final, ultimate destiny of everything. The fate of the cosmos hinges on a silent battle between two invisible titans. On one side, dark matter uses its gravitational pull to rein in the expansion of the universe, acting as a cosmic brake. On the other, dark energy pushes back, an anti-gravity force accelerating the expansion of space itself. The ultimate destiny of everything, from the largest galaxy to the smallest atom, depends entirely on the outcome of this struggle. Current observations paint a clear and somewhat chilling picture. The universe is not just expanding, it is accelerating, with galaxies flying apart from one another at an ever-increasing rate. This tells us that for now, dark energy is winning. But the role of dark matter is not over. its immense gravitational presence continues to act as a counterweight, a vast reservoir of cosmic glue that slows the acceleration, even if it cannot yet stop it. If the density of dark matter were significantly higher, its collective gravity could have overcome dark energy's push, eventually reversing the expansion and pulling the entire universe back in on itself in a fiery cataclysm known as the Big Crunch. In that scenario, time itself would run backwards, a cosmic implosion erasing all structure. In our reality, however, the balance of power seems tipped toward a different, colder end. With dark energy dominant, the expansion appears destined to continue forever. Billions of years from now, distant galaxies will be pulled so far away that their light can no longer reach us. The cosmic sky will go dark, leaving our local galactic group isolated in an immense, expanding void. This is the heat death, a slow fading into cold, dark stillness. So why does dark matter's specific nature matter for this cosmic forecast? Because to predict the final outcome with certainty, we need to know exactly how much dark matter exists and whether its properties might change over eons. Is it perfectly stable, or could it decay over astronomical timescales, further ceding the battlefield to dark energy? The answers are written in the subtle details of its gravitational influence, details we are still striving to measure. This profound connection elevates the search for dark matter from a fascinating puzzle to a quest for ultimate meaning. It ties directly into the most fundamental questions we can ask. Where did we come from? The gravitational seeds of dark matter gave birth to galaxies. And where are we going? Its ongoing tug of war with dark energy will decide the final chapter of reality. To test these grand theories of cosmic fate, we must bring the universe into the laboratory, building digital worlds to see if our ideas hold up under the relentless pressure of simulation. The most ambitious experiments in cosmology do not happen in a lab, but inside the humming memory of a supercomputer. These are cosmological simulations, vast digital universes built to rewind time and watch dark matter build the cosmos from the ground up. Projects like Illustris TNG and Eagle are their names, and their task is monumental. They begin with a virtual cosmos almost perfectly smooth, just after the Big Bang, and seed it with billions of particles, each one representing a parcel of dark matter or ordinary gas. Then they set the laws of physics in motion and let the simulation run for billions of virtual years. The supercomputers must solve the complex equations of gravity, pulling these particles together into clumps and filaments, while simultaneously calculating the hydrodynamic forces that govern the swirling, cooling, and colliding of gas. This is the core of the challenge, to marry the simple, predictable pull of dark matter with the messy, chaotic physics of the visible universe. The simulation must model star formation as dense pockets of gas collapse and ignite, and then the violent feedback from those stars as supernova explosions blast gas back out into the void, reheating it and shutting down further star formation for a time. Getting this intricate dance right is everything. When scientists compare their most sophisticated simulations to the real night sky, they sometimes find subtle but crucial differences. One of the most persistent puzzles is known as the core cusp problem. Many simulations predict that small dwarf galaxies should have a dense, sharp peak of dark matter at their centers, a cusp. Yet observations suggest many of these faint galaxies have a much smoother, flatter distribution, a core. This discrepancy is not a failure of the dark matter model, but a vital clue. It tells us that our understanding of the complex baryonic physics, how supernova and black holes can churn up and reshape the dark matter at a galaxy's heart, is still incomplete. Each mismatch between the virtual and the real universe forces a refinement, a tweak to the algorithms that govern star formation or energy feedback. With every advance in computing hardware and every clever new algorithm, these digital universes grow larger and more precise, allowing us to test different theories of dark matter by simply changing the initial rules. Does warm dark matter produce the right web of structure? Does a self-interacting dark particle smooth out those problematic cusps? These simulations are the ultimate testing ground, a collaborative masterpiece of astrophysics, computer science, and mathematics. They are virtual telescopes pointed inward, helping us decipher the silent, gravitational script of the real cosmos. This digital evidence is powerful, but to find our earliest and most pristine view of dark matter, we must look at the oldest light in the universe. This ancient light is our most direct window into the universe's infancy. The cosmic microwave background is a faint, cold glow that permeates all of space, a relic from a time when the cosmos was a mere 380,000 years old. Before this moment, the universe was a hot, opaque fog of plasma, where light was constantly scattered by free electrons. As the universe expanded and cooled, electrons and protons finally combined to form the first neutral atoms. In that instant, the fog cleared, and light was set free to travel across the cosmos for billions of years, reaching us now as a microwave whisper. This is the universe's baby picture, and it holds the encoded blueprint for everything that would follow. Satellites like the Planck mission have mapped this radiation with exquisite precision, revealing that it is not perfectly uniform. The sky is painted with tiny temperature fluctuations, minuscule variations of just 1 part in 100,000. These are the hot and cold spots, the cosmic seeds from which all structure would grow. The specific size and distribution of these spots are a precise cosmic recipe. They tell us that the ordinary matter we are made of, the atoms in stars and planets, accounts for a mere 5% of the universe's total energy content. Dark matter, the invisible scaffolding, makes up 27%, while the mysterious dark energy constitutes the remaining 68%. The patterns we see are a perfect match for a model where cold dark matter was already pulling matter together, creating the gravitational wells that would eventually trap gas and form galaxies. Without this dark matter component, the patterns in the cosmic microwave background would be entirely different, lacking the precise acoustic peaks that our telescopes observe. This fossilized light provides a robust, independent confirmation that dark matter is not only real but was a dominant presence from the very beginning. Its gravitational influence imprinted on the cosmos long before the first star ever shone. This primordial snapshot allows us to run the universe in reverse, to understand the initial conditions that set the stage for the grand cosmic drama. With this foundational evidence secured, we can turn our gaze closer to home, to the whirling dance of stars within our own galactic neighborhood. A star's path is a cosmic confession, revealing secrets about the unseen forces that guide it. Here in our own galactic neighborhood, astronomers perform a delicate census, meticulously tracking the motions of stars not just around the galactic center, but also in their vertical journeys, bobbing above and below the thin plane of the Milky Way. The speed and extent of this perpendicular dance depend entirely on the gravitational pull they experience, a pull that must come from all the mass in the vicinity. When scientists add up the weight of every star, every gas cloud, every speck of visible dust, the numbers fall short. There is simply not enough gravity to explain the stellar velocities they observe. The only explanation is a fine mist of dark matter permeating the space around our sun, an invisible presence adding its subtle but essential tug to the mix. This local measurement gives us a crucial data point, a sample of the hidden substance in our own cosmic backyard. Zoom out to the grand design of a spiral galaxy, and the evidence becomes even more dramatic. The galaxy's rotation curve, a graph of orbital speed versus distance from the center, should theoretically fall away with outer stars orbiting much more slowly than those near the bright core. But for nearly every spiral galaxy we observe, the curve remains stubbornly flat. Stars on the distant outskirts race along at the same incredible speed as those closer in, as if the entire galaxy were a solid disk. This is the classic, undeniable signature of an immense dark matter halo, a vast sphere of invisible mass whose gravity grips those far-flung stars, whipping them around on their impossible courses. Even in the seemingly chaotic blobs of elliptical galaxies, where there is no clean rotation to measure, the story is the same. By analyzing the velocity dispersion, the random variations in the speeds of thousands of stars swarming like bees, astronomers can map the underlying gravitational potential. That potential is always far deeper than the glow of the stars can account for, pointing unequivocally to a dominant halo of dark matter. These kinematic studies allow us to trace the ghostly outline of dark matter within individual galaxies, creating maps that we can then compare to the predictions of supercomputer simulations. Sometimes the stellar motions reveal new puzzles. The Radcliffe Wave, a colossal, serpentine chain of star-forming gas stretching through our galaxy, oscillates in a way that might be driven by a close encounter with a clump of dark matter, a hidden subhalo perturbing the galactic disk. Every subtle wobble and every rapid orbit helps us probe the nature of the ghost itself. Does the dark matter density rise sharply toward the galactic center, or does it form a soft core? Do its particles ever collide with one another, or do they pass through like perfect phantoms? The dance of the stars is our most direct window into these properties, a dynamical proof that the universe is filled with a mass we cannot see. This silent, gravitational choreography sets the stage for an even more exotic possibility, one where dark matter collapses into the most extreme objects imaginable. Perhaps the dark matter mystery requires no new particles at all, but something forged in the universe's first chaotic moments. An audacious alternative suggests the invisible mass could be made of black holes, but not the kind born from dying stars. These would be primordial black holes, formed in the intense pressure of the Big Bang's immediate aftermath. Imagine the infant universe as a seething, dense soup, not perfectly smooth, but rippling with tiny variations in density. In the most extreme of these dense spots, gravity could have won an instant victory, causing pockets of space to collapse directly into black holes. These primordial objects could range in mass from less than a tiny asteroid to many times the mass of our Sun, all formed before the first stars ever flickered to life. If they were produced in staggering numbers, their collective gravitational pull could perfectly account for the dark matter we infer. This idea, once on the fringes, has been jolted into new relevance by the detections of the LIGO Observatory. When LIGO heard the space-time ripples from merging black holes, some of those black holes were surprisingly heavy, falling into a mass range that makes some scientists wonder if they were not stellar remnants at all, but these ancient primordial relics finally announcing their presence. Yet the cosmos itself places strict limits on this provocative idea. Surveys like the Ogle project have spent years watching millions of stars looking for a telltale flicker. If a primordial black hole were to pass directly in front of a distant star, its gravity would act as a lens, briefly focusing the star's light and causing it to brighten. The fact that we have not seen nearly enough of these microlensing events tells us that primordial black holes cannot make up all of dark matter, at least not within a wide range of masses. Similarly, the pristine pattern of the cosmic microwave background would be subtly altered if too many of these black holes were present, effectively ruling them out as the sole culprit. So while a universe filled with ancient black holes is a captivating thought, the evidence suggests they can only be a small fraction of the answer, perhaps populating specific, narrow windows of mass. Their primary interaction would be through gravity alone, perfectly matching dark matter's ghostly behavior, and the very lightest of them would now be evaporating in a final burst of Hawking radiation, a potential signal we might one day detect. This non-particle approach dramatically widens the search, reminding us that the solution might be something grander and more dramatic than a single subatomic ghost. It underscores the creative diversity of thought driving cosmology forward, where every possibility, no matter how strange, must be rigorously tested. As we contemplate these primordial giants, we are pushed to an even earlier epoch, to the very trigger that set the stage for their possible formation. The very fabric of the cosmos was stretched and seeded in an unimaginably brief instant. This is the epoch of inflation, a fraction of a second after the Big Bang, when the universe underwent a violent, exponential growth, smoothing and flattening the entire cosmic landscape. But it was not a perfect smoothing. On the quantum level, tiny fluctuations were inevitable, and as space expanded faster than light, these minute ripples were blown up to cosmic proportions. These were the first seeds of all structure, the primordial blueprint for everything to come, imprinted equally upon the fields that would become both ordinary matter and the mysterious dark matter. The predictions of this theory are stunningly precise. It forecasts a specific pattern for these initial ripples, a nearly scale invariant spectrum where perturbations exist on every scale, from the size of a galaxy cluster down to a single star. And when we look at the cosmic microwave background and the vast cosmic web, that is exactly what we see. The pattern in that ancient light is a perfect match for an inflationary origin. This shared beginning, however, led to two very different journeys. Ordinary matter, the protons and electrons that make up our world, was trapped in a constant battle with radiation. For hundreds of thousands of years, the intense pressure of light pushed back against gravity, preventing gas from collapsing. Dark matter, however, was aloof from this struggle. Since it does not interact with light, it felt no radiation pressure. It was free to respond to gravity's gentle tug immediately. While normal matter was still a chaotic, glowing fog, dark matter was already quietly clumping together, amplifying those initial inflationary ripples into the first gravitational wells. This was a cosmic head start of monumental importance. Those nascent dark matter halos became the traps that would eventually catch the falling baryonic gas. Once the universe cooled enough for atoms to form and the cosmic fog cleared, this normal matter simply flowed into the waiting gravitational basins that dark matter had already prepared. The properties of the dark matter itself then dictated the character of the emerging cosmos. Was it cold, moving sluggishly, allowing it to clump efficiently into small galaxies? Or was it warm, its faster motion washing away the smallest structures? The specific tapestry of galaxies and clusters we observe today is a direct result of that choice, a frozen record of dark matter's fundamental nature. This profound link connects the most fleeting moment of creation to the universe we inhabit billions of years later. The theory of inflation makes specific predictions about the distribution of dark matter, predictions we can now test with powerful telescopes mapping the large-scale structure of space. Each new map is a direct test of our cosmic origins, tying the physics of the unimaginably small to the grand architecture of the cosmos. This hidden partnership, born from quantum ripples in the first instant of time, raises a compelling new question about the ghost itself. Does this unseen substance merely feel gravity, or does it also feel a faint echo of its own presence? the ghostly substance might not be as solitary as we once thought. For decades, the leading picture of dark matter was simple: a vast sea of particles that felt only gravity, drifting past one another in perfect, silent indifference. But what if these ghosts can sometimes touch? This is the compelling idea behind self-interacting dark matter, or SIDM. It proposes that dark matter particles can, on rare occasions, scatter off each other like billiard balls colliding in the void. This tiny interaction would not be through the electromagnetic force, of course, but perhaps through a new, unseen force specific to the dark sector itself. This single twist in the tale could solve some of the most stubborn puzzles in modern cosmology. Take the core cusp problem in dwarf galaxies. The simplest cold dark matter models predict these galaxies should have a sharp, dense peak of dark matter at their centers, a cusp. Yet observations often suggest a much flatter, more homogeneous distribution, a soft core. If dark matter particles can bounce off one another, they would naturally transfer energy from the densely packed inner regions to the outskirts, smoothing out that sharp central peak into the gentler core we actually see. It is a beautifully elegant fix, using the hidden nature of the particles to explain the shape of the galaxies they build. Galaxy clusters offer a different kind of test. When two clusters collide, as in the bullet cluster, the dark matter components pass right through, but if they were self-interacting, we would expect to see a slight lag, a subtle smearing in the dark matter maps created by gravitational lensing. The fact that we see a clean separation already tells us that any self-interaction must be very, very weak, but not necessarily zero. The hunt is on to find the Goldilocks zone, the precise strength of interaction that can solve the small-scale problems without violating the large-scale successes. This idea opens a breathtaking possibility that dark matter is not a single, simple particle, but part of a rich and complex hidden sector, with its own forces and perhaps even its own dark atoms and dark chemistry playing out in the shadows. The potential for discovery here is immense, as it would reveal not just a new particle, but an entirely new chapter in the laws of physics. This search for a hidden structure within the dark world naturally leads us to consider another set of elusive cosmic phantoms, the neutrinos, and their own mysterious connection to the missing mass of the universe. Neutrinos stream through the universe as ghostly cosmic messengers, nearly as elusive as dark matter itself. These tiny particles are produced in the hearts of stars and in the violent deaths of supernova, and they pass through our planet in their trillions every second, leaving barely a trace. For a time, scientists wondered if these phantoms could be the very substance we were searching for. Yet, we now know neutrinos cannot be the primary component of dark matter. They are simply too light and move far too quickly, a form of hot dark matter. In the early universe, this high speed would have washed out the delicate gravitational seeds of galaxies, preventing the very structures we see from ever forming. The cosmos would be a much smoother, emptier place. Still, neutrinos are not irrelevant to the mystery. They do possess mass, however minuscule, and that mass contributes a small but measurable fraction to the universe's total dark matter budget. Their presence and properties subtly influence the grand cosmic choreography, leaving a faint imprint on the large-scale structure of the universe and the patterns in the cosmic microwave background. Pinpointing their exact mass is crucial for refining our cosmological models. Experiments like Hadron are engaged in this painstaking work, using monumental spectrometers to capture the faintest whispers of energy from radioactive decay, hoping to weigh the lightest thing we know of. The quest to understand neutrinos has even led to a compelling hybrid candidate, the sterile neutrino. This hypothetical particle would be far more massive than its ordinary cousins and would interact only through gravity, making it a perfect fit for warm dark matter, a substance that could potentially solve some of the small-scale puzzles of galaxy formation. The story of the neutrino is a powerful lesson in scientific progress. It shows us how the pursuit of one cosmic phantom can illuminate the path to understanding another. While they are not the main character in our dark matter story, their discovery and ongoing study demonstrate the profound interconnectedness of particle physics and cosmology. Each mystery solved or even partially clarified tightens the web of our knowledge, bringing the larger truth into sharper focus. This collaborative dance between different fields of science raises broader questions about the value of such a profound and challenging search. What does this decades-long hunt for an invisible substance truly mean for us, for our society, and for our future on this planet? The search for the invisible architecture of the cosmos carries a visible and substantial price tag. Building machines to catch a ghost, from colossal particle colliders to vats of ultra-pure xenon buried deep underground, is an endeavor that costs billions. This immense scale naturally raises a profound and necessary question. In a world with pressing immediate needs, from climate change to disease, is it ethical to devote such vast resources to understanding a cosmic mystery? The debate touches on the very purpose of science itself. On one hand, the funds allocated to a single large experiment could transform public health or education systems. It is a valid argument that society must weigh its hunger for fundamental knowledge against its responsibility to alleviate tangible suffering in the present. Yet the history of big science reveals a different, often unpredictable, kind of return on investment. The quest to detect a single dark matter particle has driven monumental advances in cryogenics, creating methods to cool materials to near absolute zero. It has pushed the frontiers of computing, demanding new ways to process unimaginable volumes of data. The development of ultra-sensitive sensors for these experiments has already found applications in medical imaging, potentially leading to earlier disease detection. These are not the stated goals of the research, but they are its powerful and practical spin-offs, technologies born from the sheer ambition of the question being asked. This fundamental research also ignites a different, equally vital kind of fire. It captures the public imagination, reminding us that we are part of a vast and mysterious cosmos. A single image from a new space telescope or a breakthrough announcement from a deep underground lab can inspire a child to look up at the night sky with wonder, setting them on a path to become the next engineer, programmer, or doctor whose work will benefit society in countless ways. This global endeavor also forges bridges. Dark matter research is not confined by national borders. It is a collaborative human enterprise with scientists from dozens of countries working together at facilities like CERN, sharing data and insights. In a world often divided, this shared pursuit of a universal truth stands as a powerful example of international cooperation. The choice to fund such projects is ultimately a reflection of our values. It is a statement that we are a species that looks beyond immediate survival, that we are driven by a deep-seated need to comprehend our origins and our place in the grand scheme of things. This balance between solving today's problems and investing in tomorrow's understanding is a continuous and vital dialogue, one that requires an informed and engaged public to help guide it. Behind every billion-dollar machine and every complex ethical calculation, there are individuals who have dedicated their entire lives to this search. The hunt for a ghost is a profoundly human story. It is not just a tale of machines and data, but of the people who build them, the minds that interpret them, and the sheer will that sustains a search spanning generations. Vera Rubin, whose meticulous work on galaxy rotation curves provided some of the strongest early evidence for dark matter, battled not only scientific skepticism, but also the gender barriers of her time. Denied access to major observatories and often dismissed by her male peers, she persevered, driven by a conviction that the data itself would tell the truth. Her legacy is a testament to the power of quiet, determined curiosity in the face of immense obstacles. Today, that same spirit fuels researchers who dedicate their entire careers to a single, elusive goal. They spend decades designing a detector, only to see it run for years and yield a null result. They pore over vast datasets, searching for a statistical anomaly that might be a signal or might just be random noise. The emotional toll of this repeated disappointment is real, a constant companion in a field defined by what we have not yet found. Consider the team behind the LUX experiment, who lived and worked in a former gold mine a mile beneath the Black Hills of South Dakota. For months at a time, they inhabited a world of perpetual night and silence, operating their delicate instrument in a cavern kept surgically clean. Their lives were governed by the need for absolute purity, a sacrifice made in the hope of hearing a whisper that never came. This is not failure. It is the rigorous, often unglamorous work of narrowing the possibilities, of defining the space where the answer must lie. This global community, from the deep mines of South Dakota to the tunnels of Switzerland and the mountaintops of Chile, is a tapestry of collaboration. Scientists from every corner of the world share data, challenge each other's theories, and build upon both successes and failures. A null result from an experiment in Italy is a crucial piece of information for a theorist in Japan, and a puzzling observation from a space telescope informs the design of the next underground detector. This collective endeavor reminds us that science is not a solitary genius having a eureka, a moment, but a slow, iterative process built by many hands and minds. The journey to uncover dark matter is at its heart a story about people striving to push the boundaries of human knowledge. Their dedication, their resilience in the face of uncertainty, and their shared passion for a fundamental truth inspire us all to look beyond the visible world and question the nature of reality itself. From the whirling dance of distant galaxies to the faint glow of the cosmic dawn, every clue points toward the same invisible reality. We have traced its gravitational signature in the impossible speed of orbiting stars, mapped its ghostly shape through the bending of light, and seen its blueprint in the ancient afterglow of the Big Bang. This is not a single thread of evidence, but a tightly woven tapestry where galactic motions, colossal collisions, and the universe's very structure all demand the same conclusion. A vast, unseen form of matter provides the gravitational anchor for the cosmos. It is the silent partner in a cosmic dance, the architect whose hidden scaffolding dictates the form of everything we see. We have given this mystery a name, dark matter, and the search for its identity has become one of science's greatest quests. The investigation spans from the deepest mines to the farthest reaches of space, employing radically different strategies. Ultra-sensitive detectors buried underground listen for the gentle nudge of a passing particle. Telescopes scan the heavens for the telltale flash of dark matter annihilating in the void. Colossal particle colliders attempt to create it from pure energy, while sophisticated simulations model its role in building the universe. Each method probes a different facet of the mystery, creating a comprehensive net to catch a ghost. The leading suspects, particles like WIMP and Axions, emerge from elegant theories that seek to complete our picture of fundamental physics. Yet the persistent silence from our experiments has also spurred brilliant alternatives like modified gravity, which challenge our most basic assumptions about the force that holds the cosmos together. This tension is not a weakness but a strength, a rigorous competition of ideas that pushes our understanding to its limits. The fact that dark matter remains elusive does not undermine its reality. Instead, its gravitational influence is so consistently measured across so many different scales that it has become a cornerstone of our cosmic model. We know what it does, even if we do not yet know what it is. This very gap in our knowledge is what drives science forward, forcing innovation in technology and creativity in theory. It reminds us that the universe is far stranger and more wonderful than we can perceive with our senses alone. The hidden force binding galaxies together is more than a puzzle. It is a profound reminder that most of reality lies in the dark, waiting for the light of our curiosity to finally reveal its secrets. Our journey through the cosmic dark has revealed a universe far grander than our eyes can perceive. We have traced the gravitational shadow of dark matter from the whirling dance of distant galaxies to the silent architecture of the cosmic web. The evidence is a chorus of clues, each one singing the same song of an invisible presence that shapes everything we see. From the pioneering work of astronomers like Fritz Zwicky and Vera Rubin to the modern maps drawn by gravitational lensing, the case for this missing mass is overwhelming. It is the cosmic glue, the hidden scaffolding, the silent partner in the dance of the cosmos. Yet for all we know about what dark matter does, its true identity remains one of science's greatest secrets. This profound mystery fuels a global endeavor, uniting scientists in deep underground labs, at colossal particle colliders, and with powerful space telescopes in a shared quest to catch a ghost. This is more than a technical puzzle. It is a journey that pushes the boundaries of human ingenuity. The search itself drives technological revolutions, from ultra-sensitive quantum sensors to advanced computing, with benefits that ripple through medicine, computing, and our daily lives. It is a testament to international collaboration, a shared human project that transcends borders in the pursuit of a universal truth. As we reflect on this hidden force, we are humbled by the vastness of the unknown and inspired by the power of our curiosity to illuminate it. The secrets of dark matter are still waiting in the void, and the next great discovery could be just one experiment away. You are a part of this adventure. By staying curious, by supporting scientific inquiry, and by simply looking up at the night sky with wonder, you join in this grand exploration of reality. Thank you for exploring this cosmic mystery. If this journey into the dark has sparked your imagination, please like, share, and subscribe for more voyages to the edges of our understanding. The universe is filled with wonders, and the greatest stories may still be written in the unseen.